Denmark here to speak about exoplanets at his university. Those of you who look at the details of the schedule may notice that he made a mistake. We advertised him as coming from the MIT. This was indeed where he was before. Since 2014 he is in Aarhus, assistant professor, associate. And before that he was postdoc for a long time in MIT. Before that he was in Leiden doing a PhD with Snell and Andreas Böhmer in Situnia. And he was studying before that at the University of Hamburg, and I found it interesting that he also worked as a diver, as a research diver. Yeah. So you have not brought pictures from that time.
No, I haven't. I should have, I guess.
You should have, but maybe we can ask questions in the question session. So let us welcome Simon, and let's look forward to his talk.
Thank you. Thank you for the nice welcome. As said, I'm going to talk about exosolar planets and the research we're doing in Aarhus. But first, I would like to acknowledge it's this work of many people I'm going to present today. Particularly, I would like to highlight the role of Vincent van Eilen, my former PhD student in Aarhus, who's now a postdoc in Leiden, Anders Houston, Maria Short, two PhD students my group who just started, and Carolina von Essen, my postdoc. And also my former boss at MIT, Josh. Exosolar planets. So we are interested, or we focus on the architecture of these systems. Today I will particularly focus on one property, and that is the alignment, or the degree of misalignment between the orbit of these planets and the rotation of the whole star. And we're looking at this property because we think this will tell us a lot about the formation and evolution of these systems. So it's always a good place to start our journey at home. So our own solar system is very orderly. We have 4 terrestrial planets on the inside, 4 gas giants further out. All these planets orbit in nearly circular orbits in one plane, and this plane is nearly aligned with rotation with the equator of our own sun. Based on this example 1, astronomers have devised a theory about how planets form. In a nutshell, protostars form. Around these protostars, accretion disk is forming. It's in this disk that we think planets form, and it's a bottom-up approach. There's about 1% of dust in these disks, the rest is gas. There's dust, which eventually arrives to form rocky planets. If these rocky planets reach a mass about 10 times the mass of Earth, then they are able to attract gravitationally gas from the influence sphere. This way, a gas giant might form. This gas disk is only around for a couple of million years, so this build-up to this rocky cross has to be relatively quick. And it can only be quick in the outskirts of the system because there's additional rocky material, solid material available because ice is formed. It's cooler in these parts of the disk. This fits very nice with our own solar system, where we have the larger gas giants further out. What's about these guys? They do have planets. How does that look like? So this is a plot eccentricity, orbit period, in log space. This is our larger planet in our own solar system. Situation before the first planet around the Sun-like star was found. Well, this is 51 Pec. Well, it doesn't really fit here. It has a low eccentricity, but it's much further in. Other planets which have been discovered later, there are also short periods, and some of them have high eccentricity, and this only got worse. So many of the large planets we have found tend to have shorter orbital periods, they are closer in, and have high eccentricities. And we don't understand how they can directly form there. And please note that this cutoff here is due to observational bias. So people have thought how to supplement the idea we had about planet formation so it also fits these exoplanets. There are different two classes of theories how planets can, after formation, be moved inwards. And one consists of an interaction between the planet and the disk. The planet surrenders some angular momentum to particles in the disk and spirals inwards. To a much less extreme case, we think this also happened in our own solar system, but not over many orders of magnitude. Another idea is that there's some kind of dynamic interaction, planet-planet scattering, or quasi-cycles. That is, there is a third body further out on an inclined orbit which induces cycles between the orbital inclination of the inner body and the orbital eccentricity of the inner body. When this body, due to the high eccentricity, comes close to the star at periastron, it might potentially raise tides. The dissipation of this tidal energy drains energy out of the orbit, the semi-major axis shrinks, and we would lead up with a gas chamber close in orbit. How to distinguish between these theories? One way to look at this is to check for the alignment of the orbit. If the planet has stayed always in the disk because it interacted with it, we should see good alignment, just as in the solar system. For the small scattering event or quasi-cycle, we expect a broader distribution in obliquity. How to measure obliquity? Well, straightforward for our own sun, we spatially resolve it. We can look at sunspots and see how they move. Not so simple for other stars, they're point sources for normal telescopes. Or what we can do is we can take a spectrum. Stars do rotate, so part of the surface is moving towards us, part is moving away. We integrate with our telescope over the complete disk, we see broad absorption lines. So we learned something about the formation, but if we would now change the orientation of the rotation axis in the plane of the sky, we would still integrate over exactly the same stellar surface area. We would see the same absorption lines. If the axis would be inclined towards us, so we would see a more polar region, then the absorption line would be narrow. So in principle, we would have a way to distinguish good alignment or a polar configuration. But for that, we would need to know the real rotation speed of the star. It's quite difficult, but I will come back to that later. If we are fortunate enough that in these systems, the planet is seen in edge on orbit, so we will see transits, and we observe it during transit, then we will miss part of the light. So if we now integrate over the stellar surface, we miss it, so we miss here blue shifted light. And in different configuration, we would miss, the deformation would be different, and here we would miss redshifted light. We can translate this into a shift in radial velocity if we take the first moment of these lines. In this case, it will be first a positive bump, then a negative radial velocity bump. If we now have a misalignment, then the deformation, as well as the derived radial velocity, would change. This way, we can access or measure the projected obliquity. This idea is quite old, was derived at the end of the last 2 centuries ago, and measured firmly in the beta-Lyran Albrecht systems at the end of the beginning of the last century. And on the y-axis, here is kilometers per second, x-axis days, and here the orbital velocity of these binaries has been taken out. You can see first a positive bump and then a negative, the same here. Since then, not that much has happened until the first transiting exoplanets have been discovered. This is HD209. And note the change in scale. This is meter per second now. We have here the orbital velocity of the star due to its movement around the barycenter of the system. And we have this RN effect, this Tidal effect. And this is well aligned with the system. A couple of well aligned systems have been detected, but also misaligned systems have been found. This is Exo3, which I think was the first one. This is clearly a misaligned system. We found systems where the planet moves over the poles, and we found even more extreme systems where the planet moves on a retrograde orbit. That is, the star moves one way, the planet goes the other way around. What does it mean? Does it mean now that the light one travels this path and the high obliquity one took this way. Here, I thought all the measurements from as of a couple of years ago over one parameter, that is effective temperature of the star. And I only plot here systems which are in a way real hot Jupiters, that is their period is less than 8 days, and the mass is more than a tenth of Jupiter. And I also indicate some cool systems and some hot ones. And what you can see that the cool system tend to have good alignment, while there's a larger spread for hot hole stars. Around this temperature range, what happens in the stellar structure is that the convective envelope becomes thinner and thinner. Eventually, these will be radiative stars. This is important in many ways in terms of magnetic fields for the stars, but also we believe that tidal energy gets dissipated much quicker in a convective envelope than a radiative envelope. So one way to look at this would be, well, maybe these guys are well aligned, not because they had been originally well aligned, but because tides could align the orbital angle, the orbital angular momentum and the stellar angular momentum. If that's true, then planets which are either less massive or further out should also sometimes show a large obliquity, even if they're around these stars. So I now show the 4 systems which fulfill these criteria a couple of years ago. And indeed, 3 of these 4 have high obliquities. On the next plot, I show again the same systems, but on a time scale, an entitled timescale. So let me explain this. Here, on this time scale, we expect systems which, if they would have been misaligned, align quite quick. On the right side, the system here, if it would be misaligned, well, it should stay like that. And these are the 2 equations here, and it highly depends on the orbital separation, on the mass ratio, and these constants we took from synchronization of binaries, double stars. And what we can see that now these 4 outliers from the last plot fit nicely in. We have good alignment for guys on the left side. This is happy 32. That is indeed such a small error bar. The interesting thing about the system is you can see it has a split symbol. I plot the systems where the effective temperature encompasses with its uncertainty interval 6,250 Kelvin as a split symbol. So this is only a few kelvins away from my borderline. If I would have used this equation, this one would have moved there. This also shows that this tidal timescale is actually in need of an expert, of a theoretician, to improve it. Nevertheless, in this picture, we could now argue all hot Jupiters have used this path, high obliquity migration. So is that the case? Well, I had one other assumption in here, which I hadn't really spelled out before. And that is, the protoplanetary disk in which a planet formed actually is well aligned with the stellar rotation axis. This is, well, I think it's actually 6 degrees for the solar system. It's nearly true for the solar system. But since the first misaligned planets has been detected, people thought about this more. And they thought there might be this might not universally be the case. And I list here some theories. So on top of the star formation is chaotic. Stars do not form by themselves. They form in dense clusters. And the idea here, for example, is that if we have a star, the infall from its disk material onto the star has already stopped. But there's still infall from the cloud onto the disk. And this infall is oblique. Then we can tilt the disk relative to the stellar rotation. All these magnetic fields, double star, so a double star companion, according to these theories, can also tilt and it makes the disk precess relative to the stellar rotation. And there are more exotic ideas like internal gravity waves. And it's important to note that these theories, or at least some of them, work differently for low mass stars or high mass stars, or cool or hot stars. So they can in principle reproduce some of the characteristics I've shown you before. So how to distinguish? If we would have a planet forming here, migrating in the disk, this dissipates. We measure this guy and we think, oh well, this is high eccentricity migration. but it was really a more fundamental thing. It was something to do with star and planet formation. One way to look at this is looking at systems where we have two planets. They're coplanar, they migrate, the disk dissipates. If you would now measure the obliquity in here, then we would know this has something to do with primordial misalignment. If we find the system as a rule to be well aligned, then this misalignment is due to the migration of these attributes. The problem with this proposal is the detected transiting multi-planet systems are fewer than single transiting systems. So on average, these guys are fainter. And it happens to be that in these systems, the planets are also smaller. This is a problem for the measurement technique we are using because the RM signal is proportional to the surface area which is covered. Nevertheless, there have been some good systems. This is KRI-94, Theo Irano measured this, and we have been a little bit later. This is a large Jupiter, well aligned. And this is more what you get. This is 2 nights with Iris at the Keck. I now omitted here the time axis. It's very hard to know where the transit has happened. Well, this is a Kepler system, so we actually do know when the transit has happened. We can also fit our model. This is the data, this is our model. Here show only for illustration. Well, this is lambda as projected obliquity. Tends to be good alignment here. But I would say this is not very satisfying as a measurement. So now coming back to this plot, so we thought about different ways to look at this system. This radial velocity is really caused by this deformation of the line. So in some systems it's useful to look at the deformation directly. In particular in this system, because Iris is the iodine spectrograph. So only part of the spectrum is used. There's some red and blue part of the CCD, which hasn't been used by this technique. There are a lot of lines in the blue part. So what we did here, we used the course we normally use for double stars to look directly at the line chain and how the chain is doing transit. We obtain from all the lines here one high signal to noise absorption line. We stack this absorption line according to their time, and then if we subtract an out of transit model, what we should be left with is how the planet shadows part of the absorption line. So if we would have high signal to noise, this is one of our test systems, HB2, which was known to be aligned. This is 10 nanometer. This star rotates with V sun I of 20 kilometers per second. The planet transit starts here, and while it goes on, the planet moves to the red part. This projection is well aligned. And this is a system we have been interested in. We have a couple of hours before transit. During transit, one can see the faint shadow. We also get a good alignment for this one, and these two spectral regions are actually now do agree. So we believe this is well aligned. There have been a couple of people doing this business using also different techniques. There was, well, let me first explain. This is a plot from a few minutes ago, but now I introduce another angle here, which is the stellar inclination, because some of these measurements haven't measured the projected obliquity but the inclination. These are measurements using astroseismology of the star, where you have, depending on this type of splitting, you can learn about the inclination towards it. So, and it's the black symbols which are multi-planet systems. These are two astroseismic systems, and there's Kepler 30, which was the first multi to be measured, where the person used spot crossing. These are all alike. It's 5 systems. So we went out and said, okay, these are Jupiters down here. The probability that they have been drawn from isotropic distribution, so are Jupiters far away from tidal alignment, it's relatively large, 60%. For these 5 multi-planet systems, the probability that they are drawn from a isotropic distribution is about 1 in a million. The problem with this result is this is a very small sample. And sure enough, shortly after we published this, I introduced Kepler 56. Another astroseismic result, it's clearly misaligned. This also, I should highlight this result. This is Kepler 410 by my PhD student. So we have now 6 well-aligned systems, 1 misaligned. So let's take a look at Kepler 56. This is a very interesting system. It's This star is already in the red giant branch, 3.5 gigayears old, and in only a couple of million years, it will engulf first the inner, and then in 100 million years, the outer of these two planets. These two planets are on a resonance, 10.5 and 21 days, so it's a 2-to-1 resonance. And people looked at the system, and they thought, well, if we place one or a couple of outer planets, because these two inner planets are coupled so closely to each other, then this outer planet could drag one planet, which then drags the other one. So these two guys can move together, they change the orbit plane together. And this planet, actually was just last week, it was announced to be there. There was a trend already before. Since then, there have been only a few additional measurements. Was 47, it's a well-aligned system. And then there's KOI 89, which was detected by a gravity dipole. The misalignment was measured by a gravity diagram. And it's a relatively weak signal, so this needs confirmation. Because it's so difficult using residual McLaughlin or any of these other techniques on this, we would like to try a different method. And that is related to the inclination. So if we would measure precisely these lines, so the width of these lines, and we have a good and prior knowledge on the actual rotation speed on V, then we would be able to learn about sine. This idea surfaced over the last decades a couple of times, also for other systems, not only planet systems. I think the result, which was most convincing, was done by Kevin Schlaufmann a couple of years back. He phrased it like the rotation statistics better here. He simulates the V sine I, he subtracts the observed one from it, he divides this, normalizes it by the uncertainty in these two, and if theta is relatively large, well, then we have a much lower than expected rotation speed, and you see it polar. The problem with this is really getting a good simulation of V, or V sine I, is very hard. We have to know the stellar mass, its age, and getting the age of the star is very difficult. And also these models are somewhat uncertain. And measuring V sine I reliable and consistency for late-life stars is difficult too. Nevertheless, my PhD student Anders Houston thought we want to give it a go, and a good sample does actually exist. It's a Kepler sample. It's large, and we can make differential measurements. So he went into the Kepler archive, grabbed all the measurements, and then, and these are the CDFs. And here he splits the sample into the hot and the cool stars. He made to divide at 6,000 Kelvin here. And we can see that here, that's where at high rotation statistics, that's where the misaligned, potentially misaligned systems live. And there's a clear difference here, just as we have seen with other methods. We can also make this multiverse single. And we again see a difference here. And we believe this is real, while this might not be real. And let me explain. We only use validated candidates for this, validated planets. To validate a planet, there has to be a certain false positive probability. It's much easier to validate a multi-planet transiting system than a single transiting system. So single transiting system, you have to be much more stringent. That means you do normally not allow stars with high rotation speeds. It's very difficult to get precise radial velocity. And that is why we probably miss a number of fast rotating stars here. We can take only the single stars and divide at a period of 6 days. And then look, do we have, outside of the 6 days, we tend to have some misaligned system. Less so for the closer in ones. That's consistent with the tidal picture. If we now make the same cut, but only plot the cool system, there's hardly any difference. It seems to be all of these planets around the cool stars tend to be aligned. All this difference comes from the hot systems, but the cool ones tend to be, the close in ones tend to be more aligned than the hot ones. This is something Anders will work on over the next years. And I now want to change a little bit gears. And I show here all the series again, which I've plotted before. This is the ones where we think planets can change their inclination after formation, and on the right side, which is much more related to star formation in general. And as you might notice, binaries or double stars feature quite prominently here. They are important for quasar cycles and tidal friction. That's the third body, which introduces cycles and eccentricity and inclination. And then there will be tidal friction to shrink the orbit, and also in this binary star companion. So I would advocate that looking at double stars will be helpful as a ground truth and also to understand these mechanisms better. So that's why we started the banana survey. I show you these are our systems, eccentricity period, binaries are not always neatly aligned. And I showed quickly two examples. And this is the Hercules, a proton view of the system. It's a very young system, there's no planet around these. It's high eccentric, short period, and two really massive stars. The reason why we had originally looked at the system was the measured upside motion, so rotation of the orbit in its own plane, changes the periastron, is much slower than if we would only assume these guys are point sources due to general relativity. If we include the deformation due to tides and due to the equatorial bulge due to rotation, then this disagreement becomes larger and larger. This was known since the early 80s. And there have been a couple of systems in the early 80s which have seen this difference. So there was the idea maybe GR is wrong, however GR has passed numerous tests, so it's a very costly explanation for just one system. If there's a third body in the system, even a large planet, this could also cause this. But this is very difficult to falsify because finding planets around such massive stars is hard. Another more crazy idea would be that these closed binaries would have misaligned spins. And this is somewhat crazy because you have to tilt the axis more than 45 degrees because we need a retrograde contribution of the equatorial bulge because already GR was too large. Nevertheless, we looked at this and I showed you one observation during the primary eclipse, grays the data, blues the model of our foreground star, which has the same radial velocity as, or nearly the same as the background star. This is our background star, the primary. This is magnesium 2-line, and black is our overall model, and it does a very poor job at fitting our data. If we let go of the assumption of the light axis, it works much better. And this is true for all the observations during secondary primary eclipse, 4 hours before mid-transit, 4 hours after. A light model disk gives a poor fit, misaligned much better. We find minus 80 degree for the secondary star. So this was measured value assuming co-light axis. This is what we expect now, given our information from the large misalignment. We have to scale this histogram to a large retrograde upside motion, because if we would see very poor on it, the stars have to rotate very quick, giving the visa alignment. We can further constrain this because there's archival visa and I data, which actually changes over time. These guys spin around like tentacles. And now the second and the last system I want to show from this is Tidal Velorum, which is different. It has no eccentricity we can detect, and it's even closer in, even more massive, and somewhat older. This observation we actually took with Ferris, a 2.2 meter telescope in Australia. And this is all information I stack up, now grayscale. Again, the magnesium 2-line. This is aluminium 3 and silicium 2, I think. I forgot. And I will now show you a plot of the primary eclipse, where I have subtracted our model of the foreground secondary, and then I just measured the moments now, so radial velocity. And this is also misaligned. This would be our line model. So this is misaligned by minus 50 degrees. And the secondary, its projection is well aligned. And can we learn a little bit more? In this system we can. This is our data now with the primary and the secondary absorption line out of the eclipse in the rest frames. And this is data which Jakub and co-worker from Coralie. This is a couple of meters away from the Ferro spectrograph. And it gave us, only a few years earlier, you can see the primary absorption line is much broader in this data than in this data. So putting even some older data together, we have some change in Visa and the projected obliquity. And this should eventually also help us to determine the exact state of the system. And well, courtesy to David and Dolphy, we have a measurement from the spring, for summer, and now the primary axis is actually sharper than the secondary, just as predicted. Okay, this is the outcome of this. We find a couple of line systems. These could be tidally lined, maybe these are primordial aligned, and something is going on for these guys. Maybe this is quasi-cycles with tidal friction. We don't know yet. What would be an excellent target would be eccentric systems, eccentric Jupiters. If quasi-cycle with tidal friction is true, then these has to be on misaligned orbits. Unfortunately, there are only a small number of such systems. HD 806 is misaligned, but there are not many others. So we try the next best thing. We look at eccentric double stars. Such a system is available since recently from the Kepler sample. And I would also argue there's old Jupiter problems with the formation of closed double stars. These stars can't form at the orbital separations where they are, because during pre-main sequence there would have been one entity. And also people have noticed that around very close double stars there's nearly always a far-away companion, which already hints to it, polar cycles with tidal friction. So this is one result, a long number. This is a period of nearly 1 year, a very high eccentricity. This is our orbital fit. And then now, this is from the tree spectrograph. And this is data during the secondary eclipse. There is no primary eclipse in this system due to the orbital orientation. This is the broadening function, which is like a CCF. This is a primary star, which is in foreground of this guy, which is a secondary star. You can see a second eclipse going on because during blue lines are at the beginning of the night, red lines are at the end of the night, and you can see this dip. This is when we lose pulse light from the secondary because it's eclipsed. What I'm now going to show you on the next slide is only this data in the rest frame of the secondary, and I subtract the model of the absorption line. What we are left with is the shadow of the primary star. So this is the data. This is velocity space. This is time before or at the beginning and the end of the eclipse. And this is a light model. And you can see that the light model and the data do not agree very well. We have first red-shifted light missing, then later blue-shifted light missing data. The light model goes the wrong way around. And this is a misaligned model of 170 degrees. This guy with his eccentricity of 0.9 is on a retrograde orbit. And this is just the RV data. Remember, the line case would have bumped up and then down. There's also a third body in this system just recently discovered. It's not even announced yet. And we are targeting a couple of these systems over the next years. And whenever we get hold of an eccentric Jupiter, we will target that too. Now I want to shift gears to another orbital parameter. I was talking a lot about the orientation of these orbits in space. Now it's about the eccentricity or the ellipticity, how egg-shaped these orbits are. This is a plot, this is something Vincent van Eylen had, and this is a similar plot to have shown before: eccentricity, orbital period, log space, now all the solar systems. And all the exoplanet systems. Multis and singles. And what's obvious, many of these have high eccentricities. We don't see it in the solar system. Here Vincent plotted the same data over a different parameter, the mass of the planet. And now it becomes clear, well, all these guys with high eccentricities, they actually do have a higher mass. than even Jupiter. So maybe we see this difference because there's we haven't been able to measure eccentricity for low mass planets. It's difficult with radial velocity because the RV amplitude is so small. So eventually we would be able to measure with RV the eccentricities here. However, Vincent didn't feel like waiting so long. Actually, you can see here potentially trend towards low eccentricities. He uses transit durations to get a hold on the orbital eccentricity. Explain me how that is done. Let me explain how that is done. If you have a planet orbital on an eccentric orbit, then if you catch it far out from the star, its transit takes longer than if it would transit the same star with the same apparent orbital distance on a circular orbit. If you would catch it near periastron and it zips by, then the transit would last shorter than it would be on a circular orbit with the same apparent distance. So this is the only time I show equations here. Let's assume we have a circular orbit and we have a central transit. Then the distance to be passed is twice the stellar radius. The velocity, well, that is 2 pi a divided by the orbital period. So this way we can couple the transit time to the radius divided by the c major axis. We have Kepler's third law. Here we can neglect the mass of the planet. It's much smaller than of the star. Now we have here the mass of the star. We divide by the stellar volume, we have the density of the star. And we have on the other side A over R, which was related to the transit duration. We can measure for some of these Kepler stars, we can measure, thanks to astroseismology, very precise the density too. Now, if these two densities do not agree, then one of our assumptions was wrong. And hopefully it was eccentricity and not a calculation error. And this is, I skipped right to the result. This is the density ratio of these two. And the gray is the gray is what we have. Blue is the solar system. And these black dashed line, that's the RV system. You see this large spread over the ratio. So our systems have a much smaller, multi-Kepler transiting systems have a much smaller spread in density. Well, can we somehow fill this plane here? Well, what we can do, we can use the mass-radius relationship from Weiss and Marcy. This is a log space. And we can integrate over all arguments of periastron. Then we get a measure for the eccentricity. And doing this is the result for the system we have. All of these systems tend to have low eccentricity. So then we found these high eccentricities here seems to be related to the mass of the planets. And there have been now other papers which confirm this result, also using more systems and different techniques. We also look a little bit at planet detection. And we have two programs ongoing, and one is related to the K2 mission, the follow-up mission of Kepler. And we are there also particularly interested in systems which help us with system architecture. And this is such a system. The transit here was very long. The orbital period of the system is only 4.6 days. So this is an unusual long transit. Normally it's about 2 hours or 3 hours for such a system. That means that if you would stand on the planet, you would see a very large fraction of the sky would be covered by the star. R over A is 0.3. So this is slightly evolved star. This is interesting for many reasons, because there aren't that many planets around evolved star, but it's also interesting for tidal interaction. So this is our radial velocity follower. We get the mass of the planet, but the plot I really want to show here is this one. So this is an on-scale distance between the Sun and Mercury, and between K239 and K239b. So the system, the orbit will shrink over a couple of years, and we might be able to even pick that up. Systems like this should help us to learn more about how tides work. Another project is related to Mascara planet detection search, which is a line project. The PI is India Snell, they have one station on La Palma, and another one will be there in Chile, end of next year, or will ship this spring. It looks at the complete sky, and it's targeting very bright systems. And they have the first candidate, which would be the third brightest of Jupiter. And the problem with the star, as I'll show you in a second, is it's very fast rotating. RV is very difficult. So there are asked us if we could also observe this guy during a transit, measuring the Sitter-McLaughlin effect. That would be helpful because if you see it on the wide absorption line of the star you think where the planet is, it has to be on this one. It has to be on the bright star, for which you have measured already the wide absorption line. So I also would like to introduce now the Sun telescope, which is run by the University of Aarhus. It's relatively new, and it was thought to be used mainly for astroseismology. It has a wonderful spectrograph, high resolution, 1 meter telescope. But luckily they also let us do some spectra for exoplanet search. And we observed the system during one night. And so this is all the CCS of the system. So it's a velocity of a V sub I of 110 kilometers. This is at the beginning, and here's the end of the transit. And I stack them all up in time. And you might be able to see a faint trail. And if I subtract the average CCF, then here you see the planet track. So we know that this planet transit is a star with a wide absorption lines. So the star, we hope it will transit. And we also know this is an oblique orbit because it doesn't start out here and it doesn't go like this, but it gets more like this. This is also an excellent system to follow up for atmospheric studies. It's Pragus Plus or Espresso. And, well, SONG is a wonderful instrument, so if you would like to work together with us on data with SONG, let us know. I now want to introduce on this last slide a project which is run by Carolina von Essen. She designed it. It's called KYNet, Kepler Object of Interest. And she takes care of some orphan TTV system, transit timing variation systems from Kepler. And she picked systems like this one, where we have a beautiful TTV system, but the period is longer than the lifetime of Kepler. We would never be able to fully characterize these systems if we don't follow up these from the ground. And she does it. So already this one data point in the case of this system roots out a short-term period. This is a much more massive companion who creates these TTVs. And there's a couple of other things going on in Aarhus in terms of exoplanet. Mia Lundquist, who's actually now here in Heidelberg at the Landessternwarte, had a very interesting result where she showed which parameter planets, if they get too close to their star, actually lose their atmosphere. We also have a group working on characterizing the host stars. I showed you before that if we would know the mass and the ages of these stars, it would be extremely helpful. That's what these people are doing, mainly by astroseismology. We're also looking at the connection between stellar activity and the planets. And we are supporting a program at the Landessternwarte, which is run by Sabine Reff and Andreas Birnbach, where they look at planetary giant stars. And that's it. Thanks a lot.
So let me make more light. Thanks for this wonderful talk about exoplanet architecture systems. The podium is open for discussions and questions. Yes, Sasha.
So, actually, that's a very simple question. Actually, how much angular momentum of the total system is in those systems that have whole Jupiter? How much is carried by the whole Jupiter?
So you already put your, no, it's an excellent question, because you put your finger in the moon. So, I'm not sure how quick I can go back, but in the solar system, all the angular momentum is orbits. This is not necessarily the case for the many of these hot Jupiters we expect to actually spiral inwards onto their star, or depending on the lifetime of the system. And then these orbit often inside the co-rotation radius of the host star. That means they create a leading tidal bulge on the star. So the star spins more, gets more spun up, and the planet spirals more inwards. Its angular velocity speeds up, and it gets worse and worse. So there's one counter-argument, and it's a good one, against the tidal alignment theory. That is, well, if we would align the rotation axis of the stars, and we would at the same time also work on synchronization of the stars, then we shouldn't see these hot Jupiters anymore, because they would have all dropped in.
So that was actually, I mean, that
Well,
was a follow-up question. So wouldn't we expect, I mean, I don't see how you can align the star without splitting it up. So
There's Lidon, I had another reference from him. He has an idea how to do that, how basically the coupling for the alignment is different than for the synchronization. But this is an open question. I can only point you to that paper. But I think it's a very valid point, and it's one of the reasons why we think we're still in this.
So, go ahead, sorry.
So many of the techniques that we showed to look at this, especially the trail spectra and the patterns that are going through the lines as a function of the rotation of the star. I know them from the seismology part and the looking at inhomogeneities or temperature differences on the surface of the star. So isn't that something that complicates your analysis?
You mean something like it exists?
Yes, I know this kind of analysis actually to study non-radial pulsations of stars.
Yeah. Yeah. So this is great about the system. This one doesn't show it. There's a similar system like this already known for a few years. Was 33, also fast rotating, also an A star. And then there you see this beautiful waves or pulsations going over the lines. This is well, we can't see it here. If we would get higher signal to noise spectrum, maybe we see it, but it is much less in this star than for us.
So that means that you can only study the least active stars.
Well, for the obliquity measurements, it depends on the data you have. For WASP statistics, it was still easy to pick up, despite the delta scrutiny pulsation, it was easy to pick out the planet trail, because you know when it happens. So this was a measurement done by David Cameron, but for some systems, if it pulsates too much, then you are out of luck. Particularly if it's not rotating that quick, and you have to measure the radial velocity, then it gets much harder.
So let me also intersect the question, and I think it is very similar to Sasha's question. So if I talk with people who calculate rotating stellar models, they often tell me that the inner core rotates much more rapidly than the outer envelope, so there is some slip between where most of the mass sits and the atmosphere. I think you assume solid body rotating stars in most of your models. Is this a correction that should be taken into account?
Yeah, so I'm mainly concerned with the surface, because it's all what we see in these measurements.
Yes.
But another way out, although this is paradox, with angular momentum, would be that you only have the outer layer to be aligned and synchronized, which is by itself, so it's only the outer layer which is influenced by the planet, which is by itself a somewhat crazy idea. You not only have differential rotation, radial differential rotation, but also, I don't know how to name it, tilt. I don't know, I think we had this in our 2010 paper. We had a paragraph on this, or a section, and we received quite some bashing for that. So we haven't repeated it since then. But then, yeah, it would be great to learn more.
So the
data seem to suggest that the misalignment is mostly for the massive planets, right? Is it correct?
Yeah, but
So is there then an idea now why that is? Why the low mass planets are more aligned?
so the lower mass we have found often be found in multi-planet systems. So like Kepler 25. And with lower, this was a Neptune-sized planet. And then there are the astroseismic systems, which also are multi-planet systems, and there some of the mass of the planets are even smaller. These measurements are completely independent of the planet mass or size. So it's great about that. But they're not only less mass, but they're also multi-systems. So it's difficult at the moment to discipline. And maybe I should add, astroseismology, unfortunately, all the good astroseismic targets from Kepler have been published. So the people look at what you see is what you will get from Kepler data alone. So we have to wait for new data before this can be repeated.
Maybe I can insert another question before Andreas gets you mentioned about the misalignment of the disk with respect to the spin axis of the star. And that should in principle be environment dependent because the accretion rate, if you model the star cluster formation in a more turbulent complex cluster type environment, is a function of environment. So have you correlated that model with, let's say, the stellar density, with the age of the thing, with its neighborhood?
You mean if we have correlated our measurement with what we think which environment the stars form?
Yes.
No, because these are all, most of these are hat or wasp planets, all the measurement, and they're field stars.
Okay, so they're way too old.
Yeah. We would love to get measurements on younger systems, but it's hard to detect planets around younger ones and even harder to make these measurements. There are some, another way to do this, and I haven't covered it at all, is to look at actually its disks, or its relative alignment of two disks in a double star, or at the disk in outflow alignment. And there are some measurements which show, some show good alignment, some don't show good alignment. So it's unclear, I think, also from that perspective.
There are studies of protostellar outflows and disks, and whether they are aligning not in thousands of stuff.
So that complementary and should be also more done.
Andreas.
It looks a bit surprising to me that there seem to be, on one hand, very misaligned systems, very extreme angles, and on the other hand, there are all these multiple Kepler systems that are incredibly aligned with very small relative inclinations between the planets. So, do we know much about, say, intermediate cases? Something, say, is there really something like a dichotomy that we have very flat systems and very misaligned systems, or are there things that are 10 degrees? How well can we tell in this intermediate range, and do we know whether there are completely different mechanisms at work to make systems extremely flat and extremely non-aligned?
Well, the first thing, the measurement. I think it's very hard to get below a couple of degrees, even if sometimes the formal error is less. We assume solid body rotation, so no surface differential rotation, which probably is wrong for a couple of these systems. So already the measurement, I think some of the uncertainties are doubtful. And I don't think we are at the moment at a position where we reliably can go below a few degrees. The Kepler systems are special because these are also these densely packed closed systems. So they are not at all, even as a multi-systems, comparable to the solar system. And most of the orbits of these planets have been a couple of tens of days, but not more. So they might be yet different from what we see for the solar system. And I'm not sure if in this kind of picture there should be kind of a flow of systems going towards good alignment. There are also, in another prediction actually of the tidal theory, in which we also is that if you have an orthogonal line, so near 90 degrees, then there should be timescale should be very long, just because the tidal bulge is orthogonal. And you should have as many systems with 180 degrees as with 0 degrees, if there would have been a random spread. Because these systems they would first align either way, either retrograde or prograde, and then very slowly spin down the star and spin it up the right way. And at least that depends on how the theory you use. So this picture of this large spread is also not, it's very difficult to interpret it in any kind of theory. Did I answer your question?
Yeah, I guess we need to come measurements.
Say again, please.
To some extent, you need smaller error bars to really see how flat the flat systems are.
Yeah. So
the error bars are always so many degrees that you wouldn't see multiple transits.
the smaller error bars would help. And another problem is we also in nearly all systems, maybe had to be 7. There are a couple of exceptions. We only measure one quantity of the full obliquity, either the projection of the axis on the sky or its inclination. So it's only for a few systems that we have the complete information.
And we would need also to McLaughlin and measure this for smaller planets.
Yeah, that's very, very hard. Well, maybe with TESS and espresso, that should be a possibility. And there are also other techniques, one I haven't talked about, which in the future might be more helpful. Interferometry with a good high-resolution spectrograph might be helpful.
So,
just one technical question. Can you go back to the Doppler imaging map of espresso mascara or the you were saying that the system is misaligned.
Yeah.
But I mean, looking at the Doppler shadow of the planet, the transiting point is almost overlapping the zero velocity component of the Doppler shift, which means it's overlapping the projected spin axis of the star and the plane of the sky. So, I mean, unless the impact parameter is 0,
Which it is?
ID is 0.
It is, yeah, that's a piece of information I haven't given. So this goes over the crater. So this is a technical, deep technical question. If you have a system which low impact parameter means you know from transit photometry it goes over the center of the star. If it's over the crater, then the trail should go from minus V sun I up to plus V sun I. If it goes from the north and south pole, then it should all this time stay in the center. And if it retrograde, it should go this way around. So because it has, we know the low impact parameter, this difference here and this difference tells us that this is highly misaligned.
Sorry.
Yeah, no, excellent point.
good. So, before we thank Simon again, let me make 2 announcements. The first one is we go for dinner with the speaker, so if you want to join, please come down and come with us. Second, next big speaker is Ian Smale from Durham University, and he will talk about the distant universe, what Alma will tell us about starburst galaxies. So now let's thank Simon again for this very nice talk.